everyone. On behalf of Riva Engineering College, it is a great pleasure to welcome our esteemed audience to today's session. Serving the nation since 1964, Riva Engineering College has experienced tremendous growth over the years. Our college proudly holds MBA grading for 3 branches and offers both undergraduate and postgraduate programs on campus. Today's session is a part of Expert Lecture Series, an initiative by the Training and Placement Cell and Riva RECpedia. This series is designed to bring together industry leaders and subject matter experts to share their insight and experiences, providing our students and faculty with invaluable knowledge and inspiration. The Expert Lecture Series aims to foster a culture of innovation and continuous learning on our campus. By engaging with experts from various fields, we strengthen our academic community and keep pace with latest trends and developments in the industry. The mission of the Expert Lecture Series is to provide an in-depth guidance, host technical discussions, and offer strategic insights that prepare our students for successful careers. Through these expert-led sessions, we strive to equip our students with the tools and knowledge they need to excel in their professional journeys. It is the great honor and privilege that we welcome our esteemed guest today, 𝐑𝐞𝐬𝐚 𝐒𝐫𝐢𝐧𝐻 ma'am. We are truly delighted to have her with us today and look forward to the invaluable insights and wisdom she will share. Now, I would like to call Uday for welcoming our guest. Over to you, Uday.
Good afternoon, everyone, respected estimated guests, seniors, and all audience members. It is an honor to have you all here today for this special event. Today, we have a very special guest with us. It is my privilege to welcome 𝐸𝐞𝐬𝐚 𝐒𝐫𝐢𝐧𝐻 ma'am. We are incredibly fortunate to have her with us today. She will be sharing her insights on multi-physics and Modsim. We are excited to learn from her experience and gain valuable guidance from someone who has made significant contribution in her field. Please join me in welcoming 𝐸𝐞𝐬𝐚 𝐒𝐫𝐢𝐧𝐻 ma'am. Ma'am, we are honored to have you here with us today. Over to you, Anushya.
Thank you, Uday. Now, I would like to call Sarvagya to introduce our guest.
Thank you, Anushya. Good afternoon, everyone. It's an honor to introduce our today's guest, 𝐸𝐞𝐬𝐚 𝐒𝐫𝐢𝐧𝐻 ma'am, a 3D experienced Edu Sales Director at Dassault Systemes India. She leads academic transformation efforts, preparing an industry-ready workforce through experience-based learning. She holds a bachelor's in civil engineering from BITS Pilani and a master's from Duke University. With over 25 years of expertise in simulation and computer-aided engineering, 𝐸𝐞𝐬𝐚 ma'am has worked across various industries including automotive, aerospace, and civil engineering. She played a key role in establishing the abacus business in India and has held leadership roles in Dassault Systems. Today, she will speak on multiphysics and Modsim, simulation at the heart of innovation. Let's give a warm welcome to 𝐸𝐞𝐬𝐚 𝐒𝐫𝐢𝐧𝐻 ma'am. Over to you, Anushya.
Thank you, Sarvagya. Now, I would like to invite our esteemed guest to share her knowledge and experience with the audience. Over to you, ma'am.
Thank you. Thank you so much, for sharing. Well, I hope you can see my slide, but first, I would like to thank you all for inviting me and giving me a chance to, contribute to the 𝐻iRAC Jayanti Talk series. So big thank you for that. What I'd like to talk to you about today is about simulation, how it is at the heart of the innovation in the business world. In particular, I'd also touch upon how multiphysics and Modsim help in accelerating the simulation and in ensuring that it makes business decisions are impacted by the simulation results that are generated in the organization. So I'm sure you are aware that right now in the world, there are several disruptive and transformational trends happening. These are in various stages of maturity. If we take something like electric vehicles, certainly that's far, far more mature than perhaps something like personalized healthcare. But these transformation trends are impacting almost every industry in the world. among all of what all of these do is they place a higher impact on business to also to be agile. Large companies can no longer be complacent and sure about their position as leaders, because you have young startups or other organizations which are leveraging newer technology and trying to, improve on their position in the market. In particular, I would say there are two trends which are especially at the foremost. One, of course, is sustainability. Whether we like it or not, we are citizens of the world, and it is our job to take care of the earth. And more product designers realize, and it is imperative for them to ensure that their decisions are also guided by the sustainability angle. And of course, something I'm sure that all of us are familiar with is the impact that artificial intelligence could have on any and every field. And in the world of simulation, it is no different. It is how can AI be leveraged to perhaps make things more effective and efficient in the product design world as well. So with that, I'd like to come back perhaps to the basics. Any business, when it's trying to design a product or an experience, they realize that they need to be better, faster, and cheaper. Now, what do we mean by that? Of course, to attract your customer to you, to your product or to your service, you need to offer something which is better than competition. That might mean that perhaps your cell phone has a better reception, it looks cooler, is more stylish. Maybe it is that the vehicle has a better ride and handling, so this is one thing that businesses need to do to have a differentiator in their product. The other aspect is what we spoke about. There are a lot of trends in the industry. There are, you need to be first to market. You need to bring your product to market faster. And so there is an imperative to be faster to market and to leverage some of these trends that you see. And at the end of the day, the product needs to be affordable to the consumer. And at the same time, it should be such that, the business is able to turn a good profit on the product itself. So for eons, of course, better, faster, and cheaper has been one of the ways that, businesses have to operate. But while doing this, they need to meet whatever are the regulations that surround their particular product. So most of the cases you have safety regulations, which might, for instance, in the case of a vehicle, be related to crash. In the case of, say, a cell phone, it could be something related to the absorption into, the human body, because you are holding the device near your head for a long period of time. So there are safety regulations which guide the design of the product. In addition to these, there are, of course, environmental safety regulations as well, which need to be met. Consumers also have expectations, and consumers' expectation both in terms of the quality of the product, maybe the maintenance of the product throughout its life cycle, as well as the impact of the product on the environment. All of these are factors besides the traditional aspects like maybe style and look of the product, which play a role in their decision making. We spoke about the need to be faster to market, which also means that these product designs have to be done in a shorter time cycle. But not only does it have to be done in a shorter development cycle, many times people are also trying to work with a smaller group of designers and engineers. So there is also maybe a resource constraint that people have to work with. And added to that is the fact that today the products we're working on are far, far more complex, involve multiple physics. For instance, if you take an automotive, today the amount of electronics in a vehicle is perhaps far, far more than what it was 15, 20 years ago. You also want to take advantage of the latest technology, whether that is in whatever field it may be, if it can impact on your product. And therefore, even for large companies which have been designing a product for many years, and again, I go back to say automotive as an example, while companies might have very set processes for working with internal combustion engines, as they go into newer areas like electric vehicles or things related to fuel cells, some of these paradigms have to change. They have to follow maybe newer methods. They have to, some of the rules of thumb that they have used will perhaps change, and they need to incorporate new DVPs into their process. So they need to do all of this, but they also need to do it within a reduced development time. And this is true, though I've taken the example of automotive, it's frankly true for almost any industry that you choose, whether it's high tech, which of course has a very quick cycle time for new models coming out, whether it's aerospace these days, any industry, industrial equipment, consumer goods, or of course energy. There is the same kind of pressure on them to leverage the kind of trends that we saw earlier. Now, where does simulation actually come in? Well, most of these industries have already been using simulation in their design process. So it's not something that is perhaps new to them. They use it to various degrees within each industry. But what I really feel is with the kind of advances which are there, simulation can really impact the speed of innovation and can also help in better decision making, business decision making. Okay, but let's first come down to one point, which is why simulate. And by the way, here when I say simulate, I mean engineering simulation. We are talking about a scientific process and that we're following to actually capture the physical behavior of the structure and then predict how it is going to react. Okay, so for those of you, most of the time what I'm talking about is finite element analysis, computational fluid dynamics, these kind of simulations, what I'm talking about. The first reason that we simulate is to test something that you could not perhaps physically test. So what you're seeing here is an example of maybe a containment vessel in a nuclear reactor. And if you want to actually, understand when it's going to fail, you're going to have a mathematical model of it. You're going to actually create a physical model, and you can't really test a nuclear reactor every time to the point of failure the way you might in a vehicle do a car crash, physical car crash. So what you're seeing here is a case where somebody did a 1:4 model of a nuclear reactor, and even that is very, very expensive. And typically in this kind of a scheme, you might have multiple countries coming in, and they will then try and predict the behavior ahead of the physical test and use that to, validate how well they're able to predict the actual failure point. And this is one reason, for instance, to test something that you either cannot physically test or which is too expensive to be testing on a regular basis. The other aspect, of course, is to understand the behavior better and to see what you could not otherwise. So what I'm showing here, for instance, is a tire, running on water. Something that happens when it rains, your car goes on a road which has water in it. But to physically test what the pattern of treads of the tire, how they impact the flow of the water when the tire is going on the road, it's something which is far more difficult to maybe capture in a physical test. But in a simulation, it's much easier to actually capture this behavior and understand it. For instance, we could also maybe cut through the tire in a simulation and understand what are the stresses inside the tire itself, inside the rubber hyperelastic material within the carcass. That would not be something that's possible always without maybe embedding a gauge or a sensor at some point. So it also allows us to test and understand something which we may not be able to, it may not be so easy to capture in the real life. But this all makes sense only if your simulation is realistic, that it is able to predict the behavior accurately. Because when it is able to capture the right physics and predict the behavior, then you can start making decisions based on it. Okay. Once you know that you can predict the behavior, you can start playing around with changes. So you can say, hey, what if I used a different kind of material, which is maybe more more sustainable? What if for this tire I used a different tread pattern? Will that reduce the noise, and therefore, be a viable alternative for me? And therefore, it allows you to explore design alternatives, which is what we call as virtual testing in a way. And it can also allow you to study what would be its behavior under adverse conditions. And I think of that as almost like a virtual twin. So what happens if I say 20 years from now, the nuclear reactors had irradiation, some of the internal concrete strength has gone down, the thickness of the concrete internally is not of the same level as what it was when it was first built. If I have that data, I could feed that into my virtual model, and then I could predict perhaps that is that reactor safe today. And in that sense, it becomes a virtual twin where we've taken the realistic condition after 10 years and we're still using that to actually predict the current behavior or even the future behavior, that with time, at what rate is it going to deteriorate. Okay. So this is where simulation, by leveraging realistic simulation, we can actually, it allows us to innovate. A designer might have many thoughts of different materials to use, different form to use, and instead of each time creating a physical prototype, it's far easier for them to do this virtually, see the results, and it also gives them the choice of perhaps trying out many more prototypes virtually than they would perhaps be able to do in the physical real world. Now, simulation is not restricted just to a couple of industries. Certainly, it cuts across many, many industries. I already showed you examples, for instance, of a civil engineering case in the past with a nuclear reactor. What you're seeing up is a side impact of a crash test dummy. What happens if there is an impact from the side? And what you're seeing, the two videos, one is the engineering or the finite element simulation, and the other is an actual, physical test, and we're seeing the camera feed from that test. And you can see that these are well correlated. And in fact, more than visual, we also, look at it from a mathematical sense to validate that this is correlated. And like I mentioned before, simulation makes sense when it is realistic and predictive, because that's when you really gain the advantage out of it. But we spoke about automotive. For instance, if you see on the right, what you're seeing here is a human heart with all the muscles, the fibers, the tissues which would be there. This is a heart which is beating at, I think, 60 beats per minute. And what you can see are pacemaker leads in there. And so it allows them to also study what is the impact of these leads on the heart, and also, how does the lead itself behave within that. So again, a case where we're applying it to life sciences. What you're seeing at the bottom is more electromagnetics with a motor, and over here, hopefully that's playing, it's a little slow. What you can see is this is a part of France, La Défense, and you can see what happens where we've simulated if some kind of a noxious chemical is let out at that point. How does it spread across the city? What is its path? How long will it take to reach certain zones within the city? And by studying this ahead of time, by studying what could happen under different, say, wind conditions, under different conditions, hopefully it will allow, city planners to take certain preventive action much, much ahead of time, because these would be things that they will do when they are generally studying this. But you're seeing examples across different industries, and I hope it gives you an idea of how simulation is used in different places. Okay. Now, in all of these cases, we spoke about the fact that simulation's example is more the virtual testing, that it is able to allow you to replace the physical test, because by and large, it's faster to simulate virtually than to create a prototype. And it's not only faster, many times it's also cheaper. And of course, the number of different designs that you could test virtually would be far more than what you would physically. Yeah. So with this, what you're seeing is a typical cycle that takes place in industry where someone comes up with a concept, they flesh it out, they design it. And normally there would be a physical test for maybe one or two designs. We're saying let's simulate. Based on the results of the simulation, we learn, we infer, we improve our design, update it, and we continue to do this. And finally, we come up with a design we're happy with. We simulate it once, depending on the industry, physically test it, and then move. That was virtual testing. Another aspect I wanted to touch upon is virtual twins, because this is another area which is, a trend prevalent today and an area that we, at least at Dassault, work quite a bit on. What is virtual twin? It's a virtual representation of a product, process, or a whole system. Typically, it has some kind of a feedback from the physical world, which tells us what is happening. And because it's able to predict or simulate and then visualize the behavior, we can actually take that feedback and understand how this would behave, maybe in the real world, explore different kinds of scenarios, and also influence decision making. And later, maybe because it is connected to the overall life cycle of this product at a different time, hopefully with AI, you could even predict things like when you need to come in for maintenance. And so I've given an example here of a tire. We already saw that, you could have a physical tire. We have virtual tires. Now, based on certain sensors in the real world, we could send feedback and say, okay, now I'm underinflated, my treads are worn, what is going to happen in this kind of situation? And typically, maybe not a full FEA, but you might have a reduced auto model or something else, which could then flag and say, hey, perhaps it is time for you to come in and change your tires. So this is the basic idea of a virtual twin, where you use the virtual world with feedback from the real world and then use that to maybe take some action and influence the real world again, based on the decisions coming out of your virtual twin. And you will see the core of this requires that you're able to predict the behavior. And that requires typically some form of simulation, scientific simulation. I'll just take a few minutes to talk about the organization I come from, hopefully not too long. But I come from a company called Dassault Systems. We are about over 20,000 people across the world, including, of course, a large R&D setup here in India, where we do, I think it's one of our largest R&Ds outside France. We focus on science and technology. And, where we are is we really believe that we can leverage the virtual world to understand and improve, the real world. And that's the core belief of Dassault Systems. We have several products and several brands. I hope some of you at some stage or the other have encountered some of our products. For instance, SolidWorks, CATIA, maybe BioVia, or if you take Simulia, you then have Abacus and few others. But the core of our work is our 3D experience platform that I'll speak about. But if you see here, we look at what we call modeling apps on the one sector. We look at simulation apps where we think of V plus R, which is where we're connecting the virtual world with the real world. And then we have things related to information intelligence, where your data sciences come in, your AI and other aspects come in. And at the underlying layer, of course, is the collaboration across all of these different layers across people who are leveraging our platform. And this is available. We work across 12 industries. We're well established in these. I'm not going to take too much time, but I did want to speak a little bit about our 3D experience platform, which we see both as an operating system and as business model. It basically is a single source of truth. I spoke about the collaboration angle, but we also, from a simulation perspective, think of it as something which can go from different scales, so multiple scales across multiple physics and domains, because this might be needed to capture that real world behavior that we spoke about in the virtual twin. So you could be at different, maybe you're looking at a system level for an overall structure. Maybe you're looking at, say, a road network throughout the country. That would be a system level. You could be going down to a little more physical level where, let's say, you're looking at the behavior of maybe a vehicle, and you're trying to go into maybe the metal behavior. And then you could go into a micro scale, a molecular level, where you're looking at how the steel behaves itself. Okay, so this would be scale and across physics, so whether it's structures, thermal, electromagnetics, fluids, and much more acoustics and so on. And our aim with the platform is to provide these physics, many ourselves, sometimes with partners, but also allowing for a seamless way to go across these, because you will need multiple physics sometimes based on the kind of product that you're working in. Okay, and I'm not going in too much into this, but these are, for instance, some of our own products when we are looking at fluid structures, etc. So you have Abacus, 𝑖𝑠𝑡, SIMPAC, and more. Okay. Now coming back to the idea of simulation and why, I hope you got an idea of why I said it's at the heart of innovation, and why it becomes that the decisions made on the product will be influenced by the results of the simulation we give. But one of the things is, where does simulation actually happen? So typically, if you take where engineering is and over the time period, normally what happens is that at the a designer works at the concept stage. There is some preliminary design, but most of the simulation actually takes place when you have a detailed design. So at the detailed design is then you might build a physical prototype, or from a virtual prototype, you kind of realize that you need to make changes. But by then, the cost of making those changes has gone up because various other decisions have already been taken. In addition to that, what you also see besides the cost is that your freedom to make these changes is also limited, because by this time a commitment has been made to various other departments and they have done their own work based on the decisions taken up front. So not only is it the cost of making a change, but it's also the number of choices that you have on what you can change becomes limited. Instead, if you work at, and that's what you're seeing here, that the later and later you are in the design cycle, the change becomes more and more expensive, and the number of decisions you can change actually becomes maybe in a way less. On the other hand, if you go to the left segment, and that's why it's called left shifting, if you do more of this at the conceptual and preliminary design stage, then you have more freedom because the commitments are less. All the departments are still speaking to each other. You have more freedom of choice, and the expense if you make a mistake is less. And so one of the things that we aim for is to push simulation earlier in the cycle so that we can explore the design space much better. Okay. Now, it's not that this is new, but it's typically struggled because first and foremost, left shifting requires that designers feel comfortable to do some level of simulation, that it is easy for them to do, that it is in an environment that they are already perhaps aware of. Because end of the day, for designers, simulation is not their primary responsibility. And of course, they already have their own regular work to do, which is itself demanding. Right. Second, the level of physics and accuracy that might be needed at that early stage is not as high as you might need at detailed stage. But at the same time, it does have to be reasonably accurate because you're taking decisions based on it, right? So the accuracy is important, but perhaps the level of accuracy need not be as much as what it needs to be in detailed design. The speed has to be much better because you want to iterate through multiple options and then arrive at what would be the right one. Another, of course, is given that this might be a good place for us to involve automation, generative design, and other approaches to make it easier for the designers themselves and also to explore the design space effectively. So again, things like machine learning and AI may be of assistance at this stage. Next comes, once we have all of these results and certain decisions are taken, as we go into downstream processes, whether that's system engineering or detail design, it would be great if some of this work could be passed down so that the work which is an effort gone in starts as the base for the next stage of the design. So with this, we certainly feel with our 3D experience platform that we've tried to do all of this. And I'm just giving you an example here of, say, an aircraft wing profile, and where when you're looking at the profile in the early stage, you want to typically maybe look at both the structural strength, but also the aerodynamics from the airflow on the wing, and explore what should be that profile to allow us to, so that you have something which is efficient. And what you're seeing here is a way for an easy way, but reasonably accurate way for a designer to basically study the different impact. And all those different dots you're seeing here, each of them is actually a design and the result of, because a brief simulation has been done. And based on the colors, they tell us which ones are an absolute no-go, which ones are an maybe, and perhaps only the ones which are acceptable, the green ones which are kind of among the best, they can then be something that can be explored better. And it gives the a chance for us to explore multiple options. You can see from this the number of options which have actually been explored. Okay, I'm not going to go into the video. And here's another example where maybe you start with a certain concept and you allow the engineering simulation to take over what should be the actual shape. And so it is the engineering which decides, what should be the form of this structure. And what you're seeing here is that there are multiple alternatives that it may have come out with. And then the simulation is run and it comes back with the results which tell us which ones are acceptable. And then between a range of the acceptable ones, maybe there is a call taken by the human. One other aspect with all of this is that when we are designing a part, typically people design for a certain, they design it assuming certain standard, for instance, material properties. But in the real world, material properties fall within, a range. There is some tolerance because there might be changes due to the manufacturing process. Similarly, the geometry is never exact. There are certain tolerances to be taken into account. And the manufacturing process itself causes some distortion in the ultimate geometry. So one of the things that we have done is try to ensure that there is a easy or simpler way for designers to account for the manufacturing process right up front when they are looking at the design. So they can request to simulate the manufacturing process, see what kind of distortions come in, and account for it right up front during the design. And it's not that this wasn't possible in the past, but it was more about how do you make this something that is easier and faster for someone whose day-to-day job may not necessarily be this. Okay, and what you're seeing here are more examples of light weighting. Again, these are things which have come, the lattice structure and design, for instance, is created out of the engineering software itself. What you're seeing at the bottom left is a situation where the flow path is optimized to take a look at, reducing the pressure drop across that particular profile. So these are all examples where some level of light weighting and generative design is actually taking place within, for various structures that you see there. So we spoke about the need for lightweighting, the need for left shifting, and the need for democratization, where designers use, simulation upfront to make an impact. The other thing is when you go into the detailed design phase, it can also be quite a lot of effort and work. There are multiple departments. Each of these departments take data from each other from multiple sources. And so what you're seeing here, for instance, is design where the geometry is created. It's put into some kind of a PLM or drive. There's fastener information. Again, here the example is, let's say, of a vehicle where you might have wells, you might have various kinds of connections, and the information of where they should be connected, the spacing is also put in. Typically, you might have some kind of outsourced agency which is helping in creating a meshed structure, whether it's, in this case of, say, a body in white of the overall structure, taking that information from the fastener, putting that in. Then it goes over to the simulation team, where again, typically you have multiple groups. You have groups that focus on crash, someone else who's focusing on vibration and noise, someone else who's focusing on the strength, someone else on the fluids. So you have multiple teams, even within CAE, who need to work with these, whose results will influence the inputs or the starting point of other groups, and all of this then results get put into a CAE. And once this process is done, various times there might be iterations as well that take place as we try to improve the design. So you can see that collaboration becomes very essential. The need for having a single source of truth, because many times we do see people searching multiple times for information, and they need to ensure they have working on the latest. And all of this is something that we feel we are addressing with the Modsim concept in the 3D experience platform. So what happens with Modsim is unifying the modeling and simulation with a common data model. So it takes care of that single source of truth, and accounts for traceability and other aspects, and the collaboration on the 3D experience platform. And it works, of course, both with our own software, but also with third-party CAD. I'll try to give a quick example to help you understand what we mean by this. Typically, the idea here is not only do you have the geometry, you have the product configuration, because typically in a vehicle, there might be multiple variants. You may have the same platform, but you might have a sedan or a hatchback, all of them as variants of, the same vehicle. So you need to have some of these product configurations, your material data, the fastener, any kind of external information coming in from a supplier. But all of this here is maintained in a single platform. And then you of course, leverage things like automated meshing, use maybe other aspects to speed up your meshing, constraints that look at the mesh quality, run the simulation within the same thing, and then look at the scenario. What this does is it reduces that entire process we spoke about earlier from weeks to days. And this goes back to getting to market faster. We need to speed up the development cycle, and this is one way that we're helping people do that. And so what you really see is a speed up in the way this is done, inbuilt traceability and collaboration, and it's also then becomes something that users are more happier perhaps to adopt, because it makes their work easier. Just an example of perhaps the time it's taken in one particular workflow. This is not true for all workflows. Each workflow will go through its own process, and each company might have their own process. But this is an example we saw for a body in white, where we are seeing a reduction from, say, 56 days the first time to 28, and with time to 14 days using Modsim and some of the aspects that we spoke about earlier. And of course, that means that you can do more iterations. You're able to go on to the next stage of design faster, and it has a huge impact on the development cycle. So we spoke about the speed up here, but we had spoken right up front about the fact that all of this makes sense only if your simulation is predictive and realistic. And when I say predictive, what I mean is before you do a physical test, you should know that your simulation is able to capture the key factors of it within the level of accuracy that you desire. right? And so this is something that multiple aspects contribute towards making sure the simulation is predictive. But when it is predictive, then you can actually look at all of these design, exploration, and other roles. Today, because of all those different aspects we spoke about, most products have multiple physics that we are going to account for. Here we're seeing an example where maybe it's an aircraft wing, and what we're looking at is what happens in the case of flutter. So you're seeing, for instance, here maybe a structure which is, what happens to its behavior under the flow conditions. So you have a fluid structure interaction. You have what is the behavior on the structural aspect about it, and then lastly, of course, you have a control mechanism which, based on the behavior it's seeing from this side, is actually going to go ahead and apply certain controls to the flap angle, etc., to ensure that the whole structure is stable. So you're seeing that these are maybe more at a 1D level, while this is at a 3D level. It's multiple physics, and all of this is something that we have done for clients on our platform in a fairly straightforward and seamless manner. And I think that becomes the critical part, which is people ensuring that integration is seamless and easy for setting up. Another example, this is a radome. So typically, let's say you have an antenna on an aircraft. To protect it during flight, you have some kind of a dome around it to protect it. And therefore, the dome, of course, has to be such that it allows the antenna to do its work, that it's not impacting the electromagnetic performance of the antenna. So that's its first job. But what also happens when, say, during flight scenarios is you have to study what is the forces on this radome. And so you do a fluid analysis and external aerodynamics analysis to understand the surface pressure on this structure. And that then takes you into a structural analysis where you understand, is the radome actually going to buckle at the kind of forces it is seeing during flight. Another aspect could be, what if you have a bird strike on the radome? How is that going to behave? Now, in our case, you are able to do all 3 of these or 4 of these analysis within the same platform. And it also makes it that much easier because you're not perhaps always repeating some of the geometry and other information. And it's easy to pass the information down from one to the other. And this is, again, what we mean by multi-physics. It also makes it easier when you want to iterate, because you might need to explore different designs, and that's where, again, the ease of moving from one to the other becomes better. This happens across different workflows. And so another workflow that I did want to speak about, which perhaps is more current and goes back to the trends we spoke about, is when you're looking at a battery cell module pack design, right? So you might be looking at a battery system and trying to understand overall how the system works. You need to capture the cell behavior. Once you've captured that cell behavior, you might take a parametric model and do different module and pack, and you will have all of that captured. What you're seeing below is, the design at various levels with the tabs between them to study maybe the flow of whether it's liquid cooling or what air cooled, what is that behavior which is coming out of this. So you need to have the cells heating up. Is that going to end up causing some kind of a thermal runaway event? All of this has to be studied, where you're looking from maybe a cell behavior pack, and maybe at a later stage, even the overall vehicle behavior, if you want to look at maybe the cooling throughout the vehicle itself. And this is where the need for integrating across different scales becomes important. Okay. One other thing I wanted to mention about Modsim is, of course, a lot of what I've spoken about is that dark blue patch, right? Modeling, simulation, and design exploration. And that is typically the product engineering. But that doesn't work by itself. In an organization, it's part of an overall process. So they probably work a lot with physical testing, both to get the properties of the material as well as to, pass back their results and see how it compares with, say, the entire crash test of the vehicle. So there is a lot of interaction with the physical testing group. But the whole process of design is because you have a particular product and a program, and that project or program has got certain requirements. Those high level requirements have been broken down to various aspects, which then trickle down all the way down to the organization. What happens with the platform is you're able to connect each of these simulations back to a particular requirement which was needed and was one of the aspects for the overall vehicle architecture itself. And so that digital thread of where does the simulation fit in, how is it going, how does it impact, becomes much, much clearer when all of the different departments are using the same platform and you're able to trace it back. For me, it's also important because then hopefully the results of these simulations are also making an impact to whatever decisions are being taken, maybe at a program level, because this is having a direct visibility at a decision maker level where that person may not want to get into each and every aspect of the simulation, but if they do want to understand one aspect or they want to look at just a couple of trade-offs, that becomes clear to them because this information is available to them. And that's where I feel it allows simulation to not just enable the innovation, but also to influence business decisions taken by someone who may not be a simulation user themselves. Again, this basically talks about the overall different people within the organization, and that's where we see at a requirements level, there might be various requirements. For instance, in an EV, maybe the range of the vehicle, and the range might require a certain level of aerodynamic drag, and that is what is going to get passed down over to engineering, where they have to ensure that they have a certain drag, and then engineering will work on it along with design, asking for changes, and if there are issues, they might go back to project management. So what you're seeing here is, with the platform, all of these different people, stakeholders are all connected. There is a thread which connects what is a requirement and how that is connected to the architecture, how that's connected to the engineering and design, and at a level where project management can understand not only where the project is, but what are the results and what is happening at a certain level within the engineering itself. And that's what I mean by being in the digital thread. I spoke on automotive, but again, like I made the point earlier, it's not just about automotive industry. Simulation is used across multiple industries. So I wanted to give here an example of, say, an electronic device of some kind, where you could see that to create this device, there are different aspects which are involved. There is, of course, the structural aspect of, fitting these different things together. Maybe, what happens if you drop, which happens to all of us, about dropping, say, a cell phone. Is it going to withstand that? There is the electromagnetics, both for performance, are those antennas interfering with each other? Are they clear? Are they able to give a good reception? As well as what is their impact on, humans? Is it within the allowable limits? There's the because there are some of these components are plastic, there's probably an injection molding process, and there is that to be studied. There is a PCB, so you might want to look at the signal integrity, power integrity of the PCB itself. And of course, there is the thermal aspect. The thermal aspect being, something that we also have to look at in terms of the heat related to this whole thing. Okay. Now, again, over here, what you're seeing is the same, the structural integrity, the thermal management, the EMI, EMC of this overall structure, and antenna placement signal integrity. Now, why are we showing this? We're showing this because within the platform, you are able to collaborate across these different departments, because mostly the person doing structural integrity may not be the person doing the, say, signal integrity or the EMI, EMC. So these will be different engineers with different levels, different expertise in different physics, but they are able to collaborate and work together because they have to study the trade-off. And that's done in a seamless and easy manner, overall speeding up the process in that way. Okay. So, in perhaps conclusion, I think what we're trying to do is, I hope I've showed you how valuable simulation is in product design and also helping designers innovate by left shifting, doing it early in the design cycle, by democratizing it so that people who are not necessarily analysts but can benefit from simulation are able to easily access it and use it. We hope we'll have an impact. Of course, ultimately, being able to do a multi-scale, multi-physics simulation is really important. And the more predictive your simulation is, the more effective it can be in gaining your confidence and, more importantly, confidence of other departments. Virtual twins are something that we can all leverage, and virtual twin, I feel at the heart of the virtual twin is a simulation which is able to predict the behavior. Once it's able to predict that behavior, then you can start in the virtual twin playing out with different conditions and understanding how it is going to behave. And it's not just for the design phase, it's also for the entire life cycle, because more importantly, you want to understand how your product is going to behave when things deteriorate or when there is an adverse condition. Maybe there's an earthquake on the nuclear reactor we saw up front. How is it going to handle that 10 years from now? What if there are floods? Is that going to impact the soil and the foundation of the reactor again? Is that something that we can take a look at, right? And lastly, of course, there is a digital thread that is running throughout the organization, and that's what helps in maintaining various aspects like traceability, but also impacting business decisions, which is ultimately what we would want to do, right? Have engineering influence real decisions that have to be made at an exec level. And so this is also the evolution in a way of, computer-aided design. Perhaps in the past, it was just about maybe creating geometry and seeing geometry. Then from there, it moved into something where people connected it with, say, product lifecycle management, looking at specifications, and then into virtual validation and testing. From there, basically, it went into something where you're looking now at multiple disciplines, trying to use templates to automate and reach out to more people. So that's where we call it a knowledge-based engineering, where there is a knowledge which is kind of inbuilt into the system, allowing more people to use it. From there, we spoke a little bit about the whole experience, where what you're trying to do is create experience, and you're also trying to use generative design maybe to create new shapes, which are dictated more by the function of the product itself. And lastly, of course, today what we have is cognitive engineering, where by tapping machine learning and AI, we can actually see how we speed up this entire process so that we have more things upfront at conceptual level faster. We are also able to leverage, say, virtual twins further down in the life cycle of the structure itself. So not just at the design phase, but further in its life cycle. So this is, what I had. If you're interested to know more, if you want to know more both about our company or about some of what I spoke about, there's a lot of information we have on what we call our communities. You don't have to be a user. It's more for you to just figure out what we as a community are talking about some of these areas. So I've put up, you can go to the Dassault website, search for communities, and the 𝐬𝐚ulia community speaks more on simulation. The Modsim community speaks about that integration of modeling and simulation that I spoke about. So feel free to go there if you want to know more. But with that, I'm done. Thank you. Thanks once again for inviting me to the REWA team. And thank you to all of you for patiently listening. That's what I had.
Thank you so much, ma'am, for taking the time to be with us today and sharing your valuable insights. Now we will open the floor for the questions. I would like to invite Yatan to ask questions from the audience. Over to you, Yatan.
Good evening, ma'am.
Good evening.
Ma'am, my name is Jatan Sharma, and my question is that how do multi-physics simulation improve the accuracy of problem solving in real world?
Okay, sure. Thank you. So, you don't need to do multi-physics for the sake of doing multi-physics simulation, but many workflows, you have two physics working together. And in such a case, you probably need to account for it. Let me maybe think of, let's say an example might be one of the examples we saw, right? If you're looking at just doing let's say your vehicle, and I'm choosing a car or a cell phone because those are things people perhaps you see in your day-to-day life. But for instance, okay, if you just want to understand the drop test of your cell phone, you just want to drop it, it's just structural, right? The electromagnetics has no influence on how it's going to fall or whether it's going to crack. So when you do a drop test, it's sufficient for you to actually only consider the structural behavior. But let's say you want to study the heat coming out of your cell phone, because after we speak for some time, many of these cell phones are becoming warm, right? And you want to study that. Then you have no choice. You have to study the flow characteristics in terms of, say, CFD. You might have to study the electromagnetics, because that electricity and the electromagnetics is also causing certain thermal behavior. So now you might have you have multiple physics involved, and you cannot get away by saying I will do only one physics. So I would say, depending on the problem, multi-physics is required to capture what is happening, and in that case you should do it.
Okay, ma'am. Thank you, ma'am.
Thank you.
I believe Ayush also has a question.
Am I audible, Anushya?
Yes, you are.
And good afternoon, ma'am.
Good afternoon.
Ma'am, I would like to ask you that what inspired you to transition from civil engineering into simulation and computer-aided engineering?
Okay, so I guess I didn't think I did a transition, but it happened. So I was a civil engineer, and I, spent a year, in fact, designing foundations and working in Engineers India, where we also used FEA. We used FEA as part of our work. FEA is also used in civil engineering. That's how I used it. And after my master's, when I joined Abacus, while we work quite a bit, we work across different industries. So at Abacus, I wouldn't say I don't any longer do civil engineering work. We also have civil engineering clients who use us for, say, tunneling, for seismic analysis, for dams, etc. But a large part of the work is automotive, aerospace, and these days I would say high tech. So it was not a conscious decision, but it was something. And I think it's always exciting to learn new things. So it's always nice to see a new industry. So today, if you ask me, I also enjoy seeing consumer packaged goods. I enjoy seeing life sciences, because that also becomes a change from the planes and cars, right?
Thank you, Ayush. Ma'am,
Thank you, ma'am. I would like to ask one more question.
Sure.
Ma'am, could you share some key moment that shaped your journey in working up the Abacus business in India?
Uh, Sure. And can I ask, in key moments, what are you, do you have a particular thing in mind or in general?
Ma'am, something extraordinary happened, or ma'am, you do something special or creative things.
Okay, sure. That is a tough one. So I'm trying to think. I think for me, so first and foremost, I was lucky enough to be given the choice of coming to India and starting the business here. So it was a big change from me, from being a technical support engineer where I had worked only on the technical role, to moving to something which was sales. And I literally had not seen a price list till I came back, because I only worked on the technical aspects. So for me, I think that was itself in a way a key moment. I think when you work with clients and there are certain, how do I put it, when you've worked with a client for some time and helped them realize a difference, then you feel it is a key moment. And you don't always hear about it, because so at Dassault, we have a team, a technical team, which helps our clients after we've sold the software and as they are using our software. Unfortunately, people typically end up calling you when they have a trouble. You help them solve that trouble, but you don't always hear the full story, though we do know many of our clients. So I think for me, I would say key moments from a client perspective, if I see, have been times when clients have come back and explained to me that, hey, for instance, when there was one tire customer who said, we were able to predict a certain issue with the tire, and when it was physically tested and that was proven, then our management really got that confidence that yes, this is technology that can actually work. So you feel that you've made a business impact. Another time, for instance, was when we spoke with, I went to visit a client whom we know well and we work with, but the testing team wanted to meet me. And I was very confused, because we only typically work with the simulation team. But it was very interesting, because the physical testing team had seen the simulation results and they were quite excited that it was so predictive and realistic. And they wanted to actually sit across, understand, and also see how they could leverage this more. So I think some of these things where you make some difference, it helps. And so for me, I would say those are for me key, because I enjoy that. I think certainly whenever we work with certain life sciences accounts, that's always also extra interesting for me. Thank you.
Thank you.
Thank you, Ayush. Ma'am, I'd like to ask a question as well.
Sure.
As a
Go ahead.
women leader in technical field, what advice would you give to young women aspiring to pursue engineering or leadership roles?
Okay. So hopefully engineering is already done, because you guys are already, or girls are already in college.
Yes, ma'am.
So I would say you have to follow your passion. And I think that I hope that today's world, there is less need to prove yourself just because you are a woman. I think almost any field and any organization, I hope there are enough women leaders and women engineers out there, that you don't feel separate and singled out. I would encourage that we should do what we want to do. Follow your passion. It doesn't matter what the gender is. I think, and I mentioned this in the past, I think the toughest time for a woman is more when you have a child, because at that point you also have a commitment to someone else. And right or wrong, around the world, women do bear a little more of the brunt of both homemaking as well as child rearing, and at a later stage maybe even elder care. And so I think it's important at that time to kind of maintain that balance. It can be very tough in the initial age, but I think if you can stick it out during that initial period, you will reap the benefits. And I think it's important for children as well. They grow independent when they see the woman going out, and they kind of learn to manage. And so I think that particular period is perhaps a little tougher for women, but we are very lucky in India that we have family, we have help that we can afford, who can contribute at that time. So I certainly hope that, today women don't feel that they are impacted by their gender, that in organizations this is not happening. And if it is happening in organizations, there are many mechanisms both within organizations as well as in government to, help ensure there is no discrimination. And I think today, when I see the world, there are so many people in any organization where we do see women. So hopefully they can just follow their passion. And yes, I would say the first few years of when you're starting a family can be difficult. So then you kind of really have to balance to the best way of what makes sense for you. There's no right or wrong decision. It's what each person chooses to make at that time.
Thank you so much, ma'am. I believe we are done with the questions. Yatin, do you want to ask a question?
Yes.
Okay, please.
Uh, Ma'am, my second question is, what industries are seeing the most significant impact of Modsim techniques today?
Okay, that's a tougher one. I would say we see it across industries. It's perhaps more organizations, because it depends on the organization. But let me put it this way. I would think if I really had to, I would say it will be, while it's applicable to aerospace, automotive, across industry, energy, everywhere, I think it is easier in younger industries. When I say younger, they're not younger in other sense, but they're younger to simulation. So if you take auto and aero, they have been in simulation for a long time. There is a lot of legacy, and with legacy, there is also always a bit of a hurdle in making a change, in transitioning. Right. So what I see is startups, newer organizations are able, even in automotive and aero, are able to leverage this technology faster. And if I go to newer industries for simulation, like say consumer packaged goods or life sciences, it is easier again for them because there is less legacy. So I see those starting off with, Modsim, and able to leverage that behavior, that faster.
Okay. Thank you, ma'am.
Thank you.
Thank you again, Yatin. Now I would like to call Ayush for the vote of thanks. Over to you, Ayush.
Thank you, Anushya. And good evening to everyone present here. As we come to the conclusion of this insightful session, it is my privilege to express gratitude on behalf of our entire community. First and foremost, I would like to extend a heartfelt thanks to our esteemed speaker, 𝐸𝐞𝐬𝐧𝐿 ma'am, for sharing her deepest insight on multi-physics simulation at the heart of innovation. Your extensive experience and expertise in simulation technology have given us a new perspective on how simulation act as a gateway to innovation. Your ability to connect complex concepts to real-world applications has truly enriched our understanding, and we are incredibly grateful for the knowledge you have impacted today. A special thank you to the training and placement cell and RSCPTA team for organizing this event and ensuring its smooth execution. Your dedication and hard work behind the scenes have made this session a successful. I would also like to extend my appreciation to all the students, faculty, and alumni who take the time to join us today. Your active participation and engagement have added to this session, making it even more impactful. Last but not least, I hope everyone of simulation technology and its role in driving innovation industries. Thank you all once again, and we look forward to see you in our upcoming sessions. Have a great evening ahead. Over to you,
Thank you,
Anushya.
Ayush. Thank you, Ayush. Now I would like to request everyone to please turn on their cameras for the snapshot. Vishal, please let me know when it's done.